Now we start part C, heap sort. Part C.1, heap nodes in each level. In order to do the analysis, because we need to estimate the efficiency. So we need to understand this topic, the number of heap nodes in each level. So the binary tree structure, we have many different levels from bottom to top. Now we want to calculate the number of nodes in each level. So then we can estimate build cost. When we build a heap, how much do we need to pay that cost? All right, so let's start. First, the bottom level, number of leaves in a heap. So let's do that first. Describing leaves. First, we need to use formula to describe leaf nodes, leaves. All right, so let me just use an example. So we did in a previous video, this example. From this example, you can see how do we describe a leaf node? How do we use formula to describe a leaf node? So what is a leaf node, right? Nodes without children. All those nodes without children. That's the leaf nodes. But how do we use indices? Indices to describe those nodes, right? In what range for their indices? That's the question. All right. Let us look at the parent-child relationship. The general parent-child relationship. Parent, A of I, index I, child, A of 2i. Here, we didn't use A of 2i plus 1, right child. So here we use the left child. Why left child, not right child? Because if a node has a child node, it must have the left child, but not necessarily right child, right? For example, this node, it has left child, but it does not have right child, right? So we cannot use the right child here, but we can use left child. If it has a child, it must have a left child. So that's the simple fact we have. Now, the question, how do we describe a node without children, without child? Okay, how do we describe it? Here we use this way. If the index of its left child, 2i, is out of bound of the array, right? For the array, current array, there is a bound, right? N, between 1 and n. Index I value, we do not count 0, right? We ignore, we skip 0 location. I should be between 1 and n. N is the upper bound, right? N is the upper bound. Out of bound means 2i is greater than n. Then out of bound. Then that means A of I has no child. All right, so let's write that expression. Meaning of no child. Condition, I less than or equal to n. So I, the node index or node location index, is within the bound, less than or equal to n, within the bound. But if we double it, 2i is out of bound, strictly greater than n, out of bound. That's the way we describe index of a leaf node. All right. Then, now let's simplify it. Here we know the range for I between 1 and n, inclusive. When we do division, divided by 2, both sides of that inequality, n over 2 is strictly less than I. That is the relationship. That's the simplified inequality. All right, so now, what is the smallest such I? We want to find the lower bound set for I that satisfies this inequality. The smallest I lower bound, floor function of n over 2, floor function plus 1. Why plus 1? Because this strictly greater than plus 1. So you can think about, okay? When n is even number, odd number, so try to think about, plus 1. Even number, strictly greater than, right? Even number, this n over 2 is an integer, but our I should be strictly greater than that. So that's why plus 1. Odd number, n over 2 is less than n over 2, floor function is less than n over 2, right? So then that smaller integer plus 1, that is greater than, strictly greater than n over 2. So you can verify it. You can easily verify that inequality relationship. All right, so after that, we can write the range for the index I corresponding to the leaf nodes. So that is floor function of n over 2 plus 1 less than or equal to I less than or equal to n. So the range here is clear. If we count the number of indices in this range, how many? The answer is n minus floor function n over 2. N minus, okay? Because this plus 1, that's included, right? That's included in I. So when we minus, we need to minus the number before it, before this number. When we use the upper bound to minus, we should not minus the lower bound directly. We should minus the number before it. 1 before it. Okay? So that's this number. N minus floor function of n over 2. This is the number of leaves. So here for this topic, there are two expressions you need to know. One is the range expression. Another is the number expression. Number of leaves expression. Two formulas you need to know. All right, so then this expression can be further simplified as one formula, one term formula. So that is ceiling function of n over 2. Ceiling function. Why is that? Here we use the formula on our textbook, page 477. We have this formula. Floor function of n over 2 plus the ceiling function of n over 2 equals n. So that's why we use n minus one of the two terms equals the other term. All right. Okay. Here we complete this part, number of leaves in a heap. But that's not enough. So we need to do more, next level, level by level. So the next level, so let's look at number of internal nodes with height 1, height concept. So here, so let me explain the height concept. So what is the height concept? Yeah. All right. Let's look at these nodes in red circles. These nodes has this property. When we start from these nodes and follow a path to the bottom leaf nodes, after one edge, so here, one edge, we reach the leaf. One edge, we reach the leaf. One edge, here, one edge, we reach the leaf. That one edge number, that's the height number, height. Yeah. Why? The reason is easy, because the leaf level we treat as the ground level, zero level, right? Ground level, zero level. Then one edge higher than from the ground level or leaf level or zero level, zero height. Yeah. So leaf nodes, that's the height 0. Okay. Height 1, one edge above height 0. Okay. One edge above, yeah, edge above height 0. So height 1 level. Yeah. All right. So that's the height. Yeah. Another concept, depth. Yeah. Depth. Yeah. From the root, how many edges between root and lowest leaf level? Yeah, leaf level. So this one, 2 edges, but in this way, 3 edges. But we take the longest path. 3 edges. So here the depth is 3. So that concept, we come from top, yeah, to bottom. The depth concept, depth. Yeah. Then the height from ground level, 0 level, and moving up. Okay, yeah. Yeah, because many students ask me, when we count height, do we come from the root or we come from leaves? Yeah, based on your intuition, right? Height, we come from bottom, right? Yeah. Then the depth, now the depth of the tree, we need to cover the whole tree, right? You cannot cover just part of the tree. So this way you cover part of the tree, right? Not the whole tree. That's why we should look at the longest path from root to one of the leaves. Yeah. All right, so that's the concept. All right, so now let's do our task. Find the number of internal nodes with height 1. Yeah. First, let's look at the number of all internal nodes. How many internal nodes do we have in a heap? Yeah. So that's very simple. Yeah. We start with total nodes n. Total number of nodes. Internal nodes plus leaf nodes. That's the total. Yeah. All right. But the number of leaves we just calculated, previous slide, n minus floor function of n over 2. Yeah. Then the number of internal nodes, the offset part, right? The offset of the number of leaves with respect to total nodes. Yeah. So the number of internal nodes, floor function of n over 2. Yeah. All right. Next, now let's look at number of internal nodes with height 1. How to do that? Yeah. With the experience we have to calculate the number of leaves, now we just extend it a little bit. We can get the answer of this task. Yeah. All right, so let's look at how do we describe those internal nodes. Yeah. Here, their children are leaves. First, they have children, right? They have children, but their children are leaves. How simple is that? Okay, yeah. So let's represent their children. 2i corresponds to the index of their left child nodes. 2i must fall into the leaf range. So this is the leaf range, right? Yeah. Leaf range. Yeah. We did it in the previous slide. Leaf range. Yeah. Now from here, do division by 2. Yeah. After simplification, yeah, because I must be an integer. Yeah. So we try to get the upper bound, lower bound, the best upper bound, the best lower bound, right? For I integer. Yeah. The best upper bound after division, yeah, it must be integer, so we take the floor function. Yeah. So that's easy. But how do we see the lower bound is this? Yeah. That's a little harder to see it. That's a little harder to see it because if we take division by 2 directly, then we take the ceiling function, we should have this expression. Yeah. This expression. But then we can simplify it to get this expression. But you may ask me, how do we simplify it? Yes, that step a little harder. So you need to do discussion. Okay, do discussion. N is multiple of 4, 4k. Okay, 4k plus 1, 4k plus 2, 4k plus 3. You try all the 4 cases and verify that equality is true. You can verify it for these 4 cases. Yeah. That equality is true. Okay, so then you have that formula. Okay, so now we just take it. Yeah. So that's why we have the lower bound here like this. Yeah. All right, the final answer. The number of internal nodes with height 1, the answer is upper bound minus, not the lower bound, 1 less than the lower bound. Okay, yeah, we don't include that 1 less than the lower bound. So that's this number. Yeah, that number. Okay, so that number less than or equal to ceiling function of n over 2 squared. Not equal. Okay, not equal. Not less than or equal. Could be less than. Could be less than. Okay, yeah. How to see that? We use these 4 cases. We can see that. We look at these 4 cases, we can see that. Yeah. A little more complicated, so I do not plan to do verification here. Yeah. All right, so you just get that. Because why we want to get this inequality? Later, when we estimate the cost, we need to use this formula. So we need to prepare, for that cost estimate. We need to prepare for it. Cost estimate later. Yeah. All right. Yeah. So that's the height 1. We want to get a general height form. General number of nodes for height h. General h. Okay. General h. Yeah. All right. So let's do that. Yeah. All right. So height 0 leaf. That's height 0. Height equals 0. This formula, height equals 1. Next, any height. Height equals h. How do we get a formula? Height equal to H. Yes. So format, you can get the idea from the format here. Yeah. All right. So, but let me go through, the whole logical reasoning step. Yeah. Generalize the previous result. Number of leaves in this way. Okay. Now, that's height 0 case. Number of nodes with height 1. The range is like this, but the number is in this formula. Yeah. Height 1. Yeah. Now, next, the general case. Number of nodes with height h. Yeah. The range for those formula, range first, range, this range. Lower bound, n over 2 to the h plus 1. One more than the height h. Floor function plus 1. Yeah, that's the lower bound. Upper bound, still floor function, but h over 2 to the h. Yeah. All right, that's the range. Okay. Then the number of nodes in that range, the formula. So this is the formula. Okay, very natural. Yeah, the general case. Yeah, and we know. Yeah, for this general case. Yeah, what do we get? Ceiling function less than or equal to ceiling function, n over 2 to the h. Yeah. Later, when we estimate the cost, we need this formula, this version. We need, this version. Because it is simpler, just one term. That version, a little harder, because two terms. Okay, yeah. All right, yeah. So we finish C.1. Yeah, it's pretty long, yeah, but this is the foundation for our next level estimate. All right, so let me stop this video first.